Imagine standing inside a universe stripped of all familiar cues. No clocks ticking, no seasons shifting, no memories whispering what happened a heartbeat ago. If you watched a cloud of gas drift through empty space, could you truly tell whether the scene was unfolding toward the future or unraveling into the past? If a star collapsed into a black hole, would you know it was collapsing at all? Or could the mathematics just as easily describe that same star exploding outward from an impossibly dense core? If light from a distant galaxy reached your eyes, would you be certain that it had traveled across billions of years? Or could the laws of nature allow the same path in reverse without contradiction? These questions sound like riddles designed to confuse, yet they rise directly from the foundations of physics. We live inside a universe that insists time moves forward, yet the deepest equations we rely on suggest something far stranger. According to them, the universe does not care which way time flows. When we look at ordinary life, time seems to have a built-in direction so obvious that we rarely question it at all. People age in one direction. A cup of steaming liquid cools as heat spreads outward. Leaves fall, seasons turn, memories accumulate in the order we experience them. We describe causes leading to effects, never the other way around. But when physicists write down the core equations that govern motion or light or quantum waves, those equations work perfectly well whether time moves forward or backward. Newton motion equations allow our orbit to be rewound step by step. Maxwell equations describe electromagnetic waves that could mathematically run in reverse without violating anything. The Schrödinger equation that tells a quantum state how to evolve is entirely symmetric. None of these laws contain a hidden switch that forces the universe to choose a one-way direction. This disconnect between experience and mathematics becomes one of the deepest puzzles in modern science. How can it be that everything we touch and see behaves as if time cannot reverse, yet the underlying rules of physics remain indifferent? The tension is not philosophical. It is firmly grounded in the structure of the physical laws themselves. You can take the position and velocity of every particle in a classical system, reverse all velocities, and the future evolution of that reverse system will perfectly reconstruct its past. In principle, a shattered glass could rewind itself into a perfect, unbroken form, its molecules tracing a path back into the shape they once held. The equations would allow it. Yet in reality, we never see such things. We never expect ashes to leap back and rebuild burned wood. We never expect waves in water to gather into a neat droplet. Reality overwhelmingly prefers one direction, even though the equations do not. The only place where physics seems to pick a side is thermodynamics. The second law states that entropy tends to increase. Entropy measures how many microscopic configurations correspond to a macroscopic state. A messy room has far more microscopic possibilities than a perfectly tidy one, so it is overwhelmingly likely that any random change will make the room messier, not cleaner. This does not arise because nature commands it to be so. It arises because the number of ways to be disordered is vastly larger than the number of ways to be ordered. Entropy increase is a statistical effect, not a fundamental rule. Yet this statistical trend becomes so dominant that it defines our perception of time. The arrow of time is the direction in which entropy increases. But even this principle leaves something unanswered. Why did the universe begin in a state where entropy was so low that it had room to increase? Gravity complicates the picture in a profound way. In everyday systems, a uniform distribution of particles has high entropy. But under gravity, the opposite is true. A smooth spread of matter has astonishingly low entropy because gravity encourages matter to clump together. A cloud of gas in deep space is not in a high entropy state. It is an extraordinarily special configuration. A slight variation in density allows gravity to pull material inward, forming stars, galaxies, and eventually black holes with enormous entropy. Gravity takes what looks like order and transforms it into structure, heating some regions, cooling others, and pushing the universe towards states with vastly more possible microscopic configurations. Instead of smoothing everything out, gravity builds complexity, and in doing so, it becomes a major engine in the growth of cosmic entropy. This creates a new layer of mystery. If gravity drives the universe toward higher entropy, and if entropy increase defines the arrow of time, then the arrow of time is not written into the laws of physics, but into the conditions the universe started with. The laws allow both directions, yet the universe behaves asymmetrically. It began in a very specific, remarkably smooth state, one that statistical reasoning alone cannot easily explain. This smooth beginning ensures that entropy has been rising ever since, guiding everything from galaxy formation to biological evolution to human memory. It suggests that the flow of time is not a built-in feature of physics, but a consequence of a peculiar beginning. As we move deeper into this chapter, the puzzle comes into sharper focus. If the equations do not choose a direction, then what did? If the universe began in a low entropy state, why did it begin that way? Why is every moment of our experience shaped by an arrow that seems to come not from the laws, but from the initial conditions those laws act upon? And to understand that, we must journey backward, following the arrow to its earliest trace in the fire and smoothness of the young cosmos, where the direction of time was set not by command but by circumstance. The universe we inhabit whispers its history through every physical process, yet the direction of that whisper depends entirely on the way entropy has unfolded since the earliest moments of cosmic time. To continue exploring this mystery, we must look more closely at how ordinary experience emerges from microscopic laws that do not care about the difference between before and after. Our memories, our expectations, our entire sense of past and future arise because the macroscopic world we navigate is governed by irreversible processes, even though the microscopic world underneath remains reversible. This contrast is not just philosophical, it defines how physics understands time itself. When a person recalls something, that memory exists because the physical structure of the brain has changed, storing information in patterns of neurons and molecules. That act of recording requires an increase in entropy, which means memory can only form in the direction of rising disorder. We remember the past, but not the future because the past had lower entropy. The same physical principles govern anything that leaves a trace: a footprint in soil, a photograph capturing light, ashes remaining after combustion. Each trace points toward a lower entropy state that came before it, which is why all records point backward instead of forward. This relationship between entropy and records creates a world in which everything seems to flow in one direction, even though the underlying equations flow just as easily in both. When heat moves from a warmer object into a cooler one, the microscopic motion of molecules increases in disorder. This transition is overwhelmingly probable and results in a system with more available microstates. But if we reversed every microscopic motion of every molecule, the heat would flow backward, seemingly violating the second law, even though this reversed evolution is perfectly compatible with the equations. The reason we never see this is not because it is forbidden, but because it is fantastically unlikely. The number of microstates that correspond to a higher entropy condition vastly outweigh the number that correspond to a lower one. The universe could, in principle, spontaneously lower its entropy in some region, but the chances are so small that they may never occur, even if we waited until the universe was unimaginably old. This means that the arrow of time is not a law of physics, but a reflection of statistical probability, pinned in place by the special state the cosmos began in. Gravity deepens the mystery, even as it clarifies its shape. In a universe without gravity, entropy would naturally increase by spreading matter more uniformly. But in a universe where gravity dominates large scales, uniformity corresponds to low entropy. As matter clumps, gravitational potential energy turns into heat, radiation, and structure. A cloud collapsing into a star increases entropy. A star collapsing into a black hole increases entropy dramatically. In fact, black holes represent the most extreme entropy reservoirs known. Their entropy is proportional to the area of their event horizons, not the volume inside them. This means that a black hole containing a mass of ordinary matter has vastly more entropy than that same mass distributed in any other way. When matter falls in, the entropy skyrockets. Gravity, therefore, acts as a cosmic engine of increasing entropy, sculpting the arrow of time through the growth of structure. It encourages the cosmos to march toward clumping and complexity, amplifying tiny irregularities into galaxies, clusters, and the large-scale web of matter that spans the universe. Understanding this interplay between gravity and entropy reveals why the early universe presents such a deep puzzle. Observations of the cosmic microwave background show that the young cosmos was astonishingly smooth. Density variations were tiny, only a few parts in 100,000. This smoothness corresponds to a remarkably low entropy state under gravity. If the early universe had been even slightly clumpier, entropy would have been far higher, and the arrow of time would have been weaker or even absent. That the cosmos began in such a special condition demands explanation. Why was it smooth at all? Why did gravity have so much room to act, so much structure left to form? These questions pull us further into the heart of the mystery, directing us toward the earliest chapters of cosmic history. This first chapter sets the stage for a journey that will follow the arrow of time from its origins to its far future. The laws themselves do not pick a direction, yet the universe we observe has done exactly that. The direction we call time is a story written into the expanding fabric of space, shaped by entropy and amplified by gravity. To understand why reality flows the way it does, we must continue tracing this arrow backward into the earliest observable eras of the cosmos, where the roots of the puzzle become clear enough to confront directly, and where the universe made the choice that now defines every moment of our existence. The question of why the universe selected a particular direction in which entropy would rise leads us deeper into the strange relationship between order, disorder, and the geometry of spacetime itself. To understand this direction, we must consider not only the behavior of matter, but also the shaping role played by the curvature of space under gravity. In general relativity, gravity is not a force that pulls objects together in the traditional sense. Instead, it is the bending of space-time caused by mass and energy. This curvature guides matter along paths that appear to us as gravitational motion. When a cloud collapses into a star, or when a star spirals toward the formation of a black hole. This motion follows the natural pathways carved into space-time geometry. These processes increase entropy because they lead to more microscopic configurations, aligning the thermodynamic arrow with the geometric evolution of the universe. The direction of time in our experience is therefore intertwined with the shapes and curves that gravity produces. Yet relativity itself does not impose a direction on time. It only governs how time flows at different rates, depending on gravitational environments. Clocks deep within strong gravitational fields tick more slowly than clocks farther away. This has been confirmed through experiments involving atomic clocks flown around the planet and clocks placed at different altitudes. But these differences in the rate of time do not tell us why time moves forward. They only tell us that time can stretch or compress depending on the gravitational field. The universality of the forward direction must arise from something else. The smoothness of the early universe becomes the leading candidate, because that smoothness represents an extraordinarily special state. Under gravity, a smooth distribution of matter is highly improbable unless the universe was born this way. That improbable beginning allowed gravity to amplify tiny variations and build structures that locked in a direction for entropy to increase. This smoothness is not a guess. It is supported by precise observations of the cosmic microwave background, showing that the universe was nearly uniform in temperature and density when it was young. The uniformity is remarkable, and demands explanation. If the early universe had been chaotic, filled with large density contrasts, entropy would already have been high, and no strong arrow of time would emerge. But because it was smooth, gravity had an extraordinary amount of work to do, pulling matter into stars, galaxies, and eventually black holes, raising entropy with each step. Every irreversible process we see today traces its lineage back to that smooth beginning. The formation of galaxies, the burning of stars, the arrangement of planets around those stars, the emergence of life that relies on energy gradients. Even the operation of your own memory depends on the fact that the universe began in a low entropy condition. The arrow of time is an echo of that initial state. As we consider this picture, it becomes clear that the arrow of time is not an illusion, but a consequence of the path the universe has taken. Even though the laws of physics do not require time to move forward, the initial configuration of the cosmos and the statistical tendencies of matter under gravity guarantee that forward motion is the overwhelmingly dominant experience. The universe had only one reasonable path to follow, beginning in a smooth state and evolving into a rich and structured cosmos. That evolution wrote the arrow of time into every star, every planet, every biological system, and every human memory. To understand the modern universe with its galaxies and living beings and persistent sense of forward motion, we must now follow this arrow back to the era when everything was just beginning to unfold. This completes the foundation of our investigation. The stage is set, the puzzle is defined, and the central contradiction is clear. Time feels directional, yet the laws do not demand direction. Entropy increases, yet only because the universe began in a condition where it could increase. Gravity shapes the growth of structure, yet only because there was so much room for structure to grow. To solve the mystery of time direction, we must now turn our attention to the early universe itself, where smoothness reigned and where the cosmic arrow first emerged from the interplay between initial conditions and the laws of physics. Imagine rewinding the universe far beyond the age of stars and galaxies, past the formation of atoms, past even the first fractions of a second when space was still unfolding. As we travel backward along this arrow, everything we recognize begins to vanish. Galaxies unspool into diffuse gas, stars dissolve into clouds of plasma, planets vaporize. Eventually, even the tiny fluctuations that shape cosmic structure blur into a nearly perfect smoothness. The further back we go, the less structure the cosmos contains, until we reach a state so uniform that it defies almost every intuition about how matter behaves under gravity. In the earliest observable moments, the universe was astonishingly smooth, a condition that carries profound implications for entropy and for the direction of time. This smoothness is not speculation. It is a direct measurement written into the faint background glow that fills the sky in every direction. That glow is the cosmic microwave background. It is the cooled remnant of radiation released when the universe was young, and it serves as a snapshot of the cosmos at a time when electrons and protons first combined to form neutral atoms. When satellites such as the Wilkinson Microwave Anisotropy Probe and later the Planck mission mapped this radiation, they revealed that the temperature differences across the entire sky were only a few parts in 100,000. This means that the early universe had nearly the same density everywhere. It was balanced, almost perfectly smooth, with only tiny ripples. These ripples would later grow into stars and galaxies, but at that early time, they were barely noticeable. This uniformity presents a striking puzzle. Under gravity, such smoothness corresponds to an extremely low entropy state. A lumpy universe would have been far more typical and far more disordered. Yet the universe we observe began in this highly special arrangement. To understand why this smoothness carries such significance, we must consider what entropy means in a gravitational setting. In systems without gravity, like a gas in a box, entropy is highest when particles spread out uniformly. But gravity changes everything. A cloud of gas in deep space has low entropy when it is evenly spread, and much higher entropy when it collapses into stars or black holes. A perfectly smooth gravitational system is therefore deeply unnatural. It is the least likely state among all the possible configurations matter could have taken. And yet, this is precisely the state the universe began in. The tiny fluctuations measured in the cosmic microwave background are evidence of the seeds of structure, but the overall smoothness tells us that the early cosmos possessed extraordinarily low gravitational entropy. This is the central fact that sets the direction of time. The arrow exists because the universe had immense room for entropy to rise, and gravity ensured that it would. The evidence for this picture extends far beyond the cosmic, microwave background. Light element abundances, predicted by the theory of primordial nucleosynthesis, match observations with remarkable precision. Hydrogen, helium, and traces of lithium were forged in the first minutes after the universe began to cool. The amounts we see today agree with calculations made from the conditions of the early universe. Large-scale structures, mapped by surveys such as the Sloan Digital Sky Survey, show patterns that emerge naturally from tiny initial ripples amplified over billions of years by gravity. Baryon acoustic oscillation measurements, which track subtle sound waves frozen into the distribution of galaxies, provide additional support for the same smooth initial conditions. Multiple lines of evidence converge on a single picture. The early universe was hot, dense, rapidly expanding, and almost perfectly uniform. This uniformity is not merely a curiosity, it is the bedrock upon which the arrow of time rests. If the universe had been born in a chaotic or highly irregular state, entropy would have been high from the beginning, leaving no direction for it to rise. The very existence of time as we perceive it depends on this initial smoothness. It is what allowed gravity to sculpt structure, to turn tiny fluctuations into stars, galaxies, and eventually environments where complex systems could emerge. Every irreversible process today, from the glow of a star to the function of a neuron, traces back to this early condition. In a very real sense, the direction of time is encoded in the fabric of the cosmic microwave background. As we explore this early era, the mystery becomes deeper rather than simpler. Why was the universe smooth at all? Why did it not begin in a more typical configuration, one with far higher entropy? What physical mechanism or initial condition produced such an extraordinary state? These questions do not yet have complete answers, even though cosmology has made enormous progress. Some theories, such as cosmic inflation, attempt to explain the smoothness by proposing a rapid expansion that stretched space into uniformity. Evidence strongly supports inflation, but whether it fully explains the low entropy remains an open question. Other ideas explore deeper possibilities about the nature of spacetime itself, but what remains certain is that the arrow of time begins here, in the smooth, low entropy state recorded in the earliest light we can observe. As we continue to examine the early universe, the idea of low entropy becomes more than a mathematical detail. It becomes the defining feature of why the cosmos behaves the way it does. When we look at the cosmic microwave background, we are not merely observing faint radiation. We are seeing the universe in a moment when it was only a few 100,000 years old, a moment frozen into place as space expanded and light decoupled from matter. This radiation carries the imprint of tiny variations that would eventually become galaxies, yet the overwhelming impression is one of near-perfect uniformity. The temperature across the entire sky differs by only tiny fractions, so small that the precision instruments aboard the Planck satellite had to measure differences far below 1,000th of a degree. This astonishing smoothness means that the distribution of matter was also smooth, because temperature and density were closely linked at that time. It is this near uniformity that reveals the extraordinary low entropy state from which everything else has unfolded. To understand why such a smooth universe corresponds to low entropy under gravity, imagine a vast cloud of gas filling space evenly. In a universe without gravity, this would be a high entropy state, because particles would be spread out as much as possible. But in a universe governed by gravity, the most probable state is one in which matter clumps together into dense objects surrounded by regions of emptiness. Stars, planets, galaxies, and eventually black holes represent far more microscopic possibilities than a uniformly spread cloud. This means that the smooth, early universe was not just ordered, it was unimaginably special. It held far fewer microscopic configurations than the universe holds today, after billions of years of gravitational evolution. Gravity did not merely shape the universe, it exploited the enormous difference between the special beginning and the more probable configurations available at later times. This difference created the direction along which entropy could rise. Evidence for this view emerges from many independent observations. When we study the distribution of galaxies across cosmic distances, we find patterns that match predictions from the early ripples in the cosmic microwave background. These ripples acted like seeds, their slight overdensities growing over time through gravitational attraction. Baryon-acoustic oscillation signatures, which are subtle imprints left by sound waves in the early plasma, appear in the large-scale structure precisely where theory predicts. The match between observation and prediction is remarkable. It shows that the universe evolved from an almost perfectly uniform state into the richly structured cosmos we see today. This evolution required an arrow of time because it required entropy to rise. The smooth early cosmos could not remain smooth indefinitely. Gravity ensured that the universe would move towards states with more microstates, and that movement is the unfolding of time as we experience it. Primordial nucleosynthesis provides another line of evidence that strengthens this picture. During the first few minutes after the universe began to cool, protons and neutrons fused into hydrogen, helium, and traces of lithium. The relative abundances of these elements depend sensitively on the temperature and density of the early cosmos. When we measure the proportions of these elements today in ancient gas clouds, they match the predictions of Big Bang nucleosynthesis with striking accuracy. This agreement confirms that the early universe was not only smooth, but also governed by predictable physical conditions. The same smoothness that allowed cosmologists to calculate element abundances so precisely also underpins the low entropy that set the direction of time. If the early cosmos had been chaotic, these calculations would fail, and the observed abundances would differ dramatically from what theory predicts. This extraordinary consistency across different branches of physics points to a single conclusion. The early universe was not just uniform, it was uniform in a way that defies typical expectations for a gravitational system. That smoothness required explanation. The widely supported theory of cosmic inflation proposes that a rapid expansion stretched space so swiftly that any irregularities were ironed out, leaving behind a vast region of smoothness. Inflation explains many features of the cosmic microwave background and has strong observational support. But whether inflation itself explains the low entropy state remains an open question. It may be that inflation occurred because the universe already had certain special conditions, or it may be that inflation set the stage for those conditions. This uncertainty does not weaken the evidence. Instead, it highlights how profound the question of the arrow of time truly is. As we consider how the early universe connected to the flow of time, the central mystery becomes more precise. The universe began in a smooth, low entropy configuration. That smoothness ensured that gravity would drive structure formation, raising entropy as matter clumped together over billions of years. This rise in entropy created the direction we call time. Every star, every planet, and every biological process emerged from that slow march toward more probable states. The arrow of time is therefore not a built-in feature of fundamental laws. It is a consequence of an extraordinary beginning. To move deeper into this mystery, we must now explore how gravity turned tiny early fluctuations into complexity, and how the universe used those fluctuations to climb upward along the slope of entropy. As we follow the unfolding of the early universe, The smoothness revealed by the cosmic microwave background becomes more than a scientific measurement. It becomes the foundation upon which all later cosmic history is built. To understand how such a beginning shapes the direction of time, we must examine how gravity interacts with those early conditions. The tiny variations in density present in the young cosmos were minuscule, yet they were enough for gravity to gain a foothold. These faint ripples in the otherwise uniform sea of matter acted like anchors around which gravity could gather material. Over immense stretches of time, these tiny differences were amplified. Areas with slightly higher density attracted more matter, becoming the cradles of future galaxies. Regions with slightly lower density became vast spaces of emptiness. This gradual amplification of initial irregularities set the stage for the rise of cosmic complexity and the continuous increase of entropy. The pathway from the early smooth state to the intricate cosmic web we observe today is well supported by computer simulations and observational data. Large-scale simulations such as the Millennium and Illustris projects demonstrate how, starting from an almost uniform distribution, gravity draws matter into filaments and clusters. These simulations do not impose an arrow of time. They simply follow the laws of gravity applied to the initial conditions revealed by the cosmic microwave background. And yet, the outcome is always the same. Structure forms, entropy rises, time flows forward. The simulations confirm that the universe we see today could only have evolved from a much smoother earlier state. They reflect a natural progression toward higher entropy, driven not by any exotic force, but by the statistical behavior of matter under gravity. The growth of structure is one of the clearest illustrations of entropy at work. When a cloud of gas collapses under its own gravity, potential energy is converted into heat, increasing the randomness of particle motions. As this collapse continues, some regions become hot enough to ignite nuclear fusion, giving birth to stars. Fusion releases energy in the form of light and heat, further raising entropy as radiation fills space. Stars themselves are engines that drive entropy upward, turning ordered nuclear fuel into radiation that eventually disperses into the surrounding cosmos. Later, when massive stars reach the ends of their lives, they explode as supernovae, spreading heavy elements across space and leaving behind remnants such as neutron stars or black holes. Black holes, in particular, represent enormous entropy. Their entropy is not a measure of disorder in a conventional sense. Instead, it reflects the vast number of microstates consistent with the mass and energy hidden behind the event horizon. A universe containing black holes has far more entropy than one without them, and the early universe contained none. The journey from a smooth early cosmos to a universe filled with stars and black holes illustrates just how much entropy has risen over cosmic time. This rise gives meaning to the direction we call time. If the early state had been highly lumpy and chaotic, entropy would already have been near its maximum, and no arrow of time would be apparent. Processes would not unfold in one preferred direction. Stars would not form in the familiar sequences. Complex structures might never emerge. The universe we inhabit owes its history to the improbability of its beginning. The arrow of time is not enforced by the laws of physics, but by the extraordinary nature of the initial conditions on which those laws acted. The smoothness of the early universe remains one of the deepest unsolved questions in cosmology. While inflation offers a compelling explanation for how that smoothness arose, it does not fully settle why the universe began in a state capable of sustaining inflation in the first place. Some theories explore whether even earlier conditions shaped the entropy landscape. Others consider whether the arrow of time might emerge differently in universes with different initial states. These ideas remain speculative, but the evidence within our universe is clear. The arrow of time exists because the early cosmos began in a low entropy condition, and gravity, acting over billions of years, magnified that condition into the structured universe we see today. As we close this chapter, we stand at a turning point in the investigation. We have traced the arrow of time back to the earliest measurable conditions of the cosmos. We have seen that entropy began low and rose steadily as gravity sculpted structure. But this raises the next essential question. If entropy drives the arrow of time, and if the early universe provided the initial low entropy state, how exactly does gravity push systems toward higher entropy? What physical processes allow tiny fluctuations to evolve into stars, galaxies, and black holes? To unravel the next part of the puzzle, we must follow the influence of gravity more closely and explore how it acts as a powerful engine of entropy in the cosmos. To understand how the universe climbed from its smooth early state into a realm filled with stars, galaxies, and black holes, we must look closely at the strange and powerful way gravity behaves. Unlike other forces that spread things out or resist change, gravity draws matter together. It encourages clumping rather than smoothing. This single trait makes gravity the chief architect of cosmic structure and one of the most important engines of rising entropy. At first glance, this may seem counterintuitive. When matter gathers into a dense object, we often think of it as becoming more ordered. But under gravity, the opposite is true. A uniform distribution of matter is highly ordered and highly improbable. A clumpy arrangement with stars and galaxies and black holes holds far more microscopic possibilities and therefore far higher entropy. This difference lies at the heart of why gravity pushes the universe along the arrow of time. Imagine starting with an almost perfectly smooth cloud of matter, as the early universe once did. In that smooth state, every region has nearly the same density, and gravity has very little to influence. But the tiny fluctuations imprinted in the cosmic microwave background provide small imbalances, and gravity cannot ignore them. A region that is just a little denser than its surroundings begins to pull in matter more quickly. As more matter falls in, the pull strengthens, causing the region to grow even denser. This positive feedback is gravitational instability, a natural process in which small ripples become the seeds of immense structures. Over vast stretches of time, these initially gentle overdensities grow into clusters of galaxies, each cluster containing billions of stars. This process is not only allowed by physics, but is the overwhelmingly likely outcome when gravity acts on a smooth field of matter. As matter collapses under gravity, potential energy is converted into heat and light. A cloud of gas falling inward becomes warmer as particles pick up speed. Collisions between those particles randomize directions and energies, increasing the disorder of the system. Eventually, some regions become dense and hot enough for hydrogen fusion to ignite, giving rise to stars. Fusion is an extraordinary engine of entropy. It turns ordered nuclear fuel into radiation that streams outward into space, raising the entropy of the surrounding environment. Stars shine because fusion releases energy, and that release is intimately tied to the universe moving toward more probable states. Every star is a beacon of irreversible change, a signpost along the arrow of time. As cosmic evolution continues, gravity drives the formation of larger and more complex systems. Galaxies merge, clusters collide. The cosmic web stretches across immense distances. This evolution has been replicated in large-scale simulations that begin with the tiny fluctuations measured in the early universe. Simulations such as the Millennium Project and the Illustrious Project reproduce the emergence of the structures we see in the sky with remarkable accuracy. These simulations do not impose direction on time. They simply apply the known laws of gravity to the initial conditions. Yet the result is always an increase in structure and an increase in entropy, demonstrating that the rise of cosmic complexity is a natural and inevitable consequence of the universe, beginning in a smooth state under the influence of gravity. Among all gravitational objects, none contribute more to entropy than black holes. A black hole is not merely a dense object. It is a region of spacetime where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. The entropy of a black hole is proportional to the area of its event horizon. a result discovered through the work of physicists studying the thermodynamic properties of spacetime. This relationship shows that black holes possess enormous entropy, far exceeding that of any other known object of comparable mass. When matter falls into a black hole, the entropy of the universe increases dramatically. In terms of microscopic possibilities, the state of matter before collapse is far more restricted than the vast number of possibilities associated with the black hole that forms. Each black hole is therefore a monumental step in the rise of cosmic entropy. The growth of entropy through gravitational processes ultimately ties the direction of time to the development of cosmic structure. The arrow of time points toward the future because the universe continues to move from a smooth, low entropy beginning toward increasingly complex and highly probable configurations. Stars burn, galaxies cluster, and black holes form because these outcomes reflect the natural tendency of gravitational systems to evolve towards states with more microstates. The universe does not simply drift toward disorder. It builds structure along the way, and each structure carries within it the traces of the cosmic climb, from early smoothness to the intricate patterns we observe today. This chapter shows that gravity is not merely a force pulling matter together. It is a fundamental driver of the universe maturation, guiding the rise of entropy and shaping the arrow of time itself. To understand how time gains its direction, we must now explore not only how gravity creates structure, but also how the geometry of space-time influences the flow of time. The next stage in our journey will reveal how general relativity reshapes time without deciding its direction, illuminating the deeper relationship between gravity and the unfolding of cosmic history. Gravity influence on entropy becomes even more intriguing when we consider how it shapes the energy flow within forming structures. When a gas cloud collapses inward, the particles accelerate as gravitational potential energy converts into kinetic energy. Collisions among particles then transform that kinetic energy into heat, increasing the internal disorder of the system. This heating is not simply a side effect of collapse. It is an essential part of how entropy grows. The warmer the cloud becomes, the more microscopic configurations of particle motion become available, and the higher the entropy rises. If cooling mechanisms allow the cloud to radiate energy away, the collapse can continue, deepening the gravitational well. But radiation escaping into space spreads energy over wider regions, increasing entropy even further. Thus, gravitational collapse and radiative cooling work together to drive the universe toward more probable states, with each step leaving behind a physical trace in the form of emitted light. The formation of stars offers a vivid example of this process. When a collapsing cloud reaches a certain temperature and pressure, hydrogen nuclei begin to fuse into helium. This reaction releases energy that escapes in the form of photons and neutrinos. These particles stream outward, spreading energy across light years of space. The radiation is not just illumination, it is entropy dispersing through the cosmos. Stars shine because they are in a constant struggle to balance the inward pull of gravity with the outward push of radiation. This balance, known as hydrostatic equilibrium, allows stars to persist for billions of years. But every moment of that lifespan is marked by an irreversible flow of energy that raises entropy in the surrounding universe. Stars are therefore engines of cosmic irreversibility, gradually converting ordered nuclear fuel into disordered radiation. As the universe ages, stars of different masses follow different evolutionary paths. Smaller stars burn slowly, remaining stable for immense spans of cosmic time. Larger stars burn more violently and end their lives in spectacular explosions. These supernovae scatter heavy elements across space, enriching the interstellar medium with the raw materials needed for planets and eventually life. The process of star birth and death is deeply intertwined with the rise of entropy. Each generation of stars increases the disorder of the universe by converting matter into radiation and by reshaping the distribution of mass through explosive events. These cycles of collapse and explosion create the diversity of structures we observe today, from nebulae glowing with the remnants of past stars to galaxies filled with billions of suns. Galaxy evolution further amplifies the role of gravity in raising entropy. Galaxies do not evolve in isolation. They interact, merge, and distort one another through gravitational attraction. These interactions unleash tidal forces that rearrange stars, gas, and dark matter on enormous scales. When two galaxies collide, their stars may pass through each other without directly interacting, but the gravitational fields of both galaxies disrupt the orderly motions within them. Gas clouds compress, triggering new waves of star formation, while radiation from heated gas escapes into space. Over time, galaxy mergers transform simple structures into more complex ones, with each transformation increasing the number of microscopic possibilities. The large-scale structure of the universe, with its filaments, voids, and clusters, is the result of countless gravitational interactions that collectively raise entropy. Among the most dramatic outcomes of gravitational evolution are black holes. When a massive star collapses, or when galaxies merge and their central black holes combine, gravity reaches its most extreme form. A black hole does not merely trap matter. It traps the information about the precise arrangement of that matter in a way that drastically increases entropy. The entropy of a black hole scales with the area of its event horizon, meaning that even a relatively small increase in mass can produce a vast increase in entropy. A single supermassive black hole at the center of a galaxy carries more entropy than the billions of stars within that galaxy combined. When matter spirals into a black hole through an accretion disk, friction and heating release tremendous amounts of radiation before the matter crosses the event horizon. This radiation spreads energy outward, further raising entropy and contributing to the universal trend toward more probable states. The rise of entropy through these gravitational processes reveals why the arrow of time aligns so closely with cosmic evolution. The universe began in a smooth, improbable state. Gravity amplified small fluctuations into vast structures, each step increasing entropy. Stars ignited, galaxies formed, black holes grew, and radiation filled the cosmos. These irreversible processes created the temporal direction we experience. Every moment of cosmic development reflects the natural progression toward states with more microstates. Time, in this sense, is not a separate phenomenon, but a property of the universe journey from its low entropy beginning toward the higher entropy states of its future. To complete our understanding of gravity's role in shaping the arrow of time, we must now look at how gravity connects to the deeper geometry of spacetime itself. General relativity describes how mass and energy bend spacetime, affecting the passage of time in ways that do not decide its direction, but profoundly influence its flow. By exploring how spacetime curvature affects clocks and motion, we will uncover the next layer of understanding in the long story of cosmic time. As we watch gravity deepen its influence across cosmic scales, a final element of its behavior brings the entire picture of entropy into sharper focus. Gravity does not simply gather matter and convert potential energy into heat. It shapes the entire geometry through which matter moves, guiding the unfolding of cosmic history along paths that naturally increase entropy. When regions of higher density begin to collapse, the curvature of spacetime changes with them. This curvature determines how objects fall, how radiation escapes, and how energy flows. Even though general relativity itself does not dictate a direction for time, the changing geometry of spacetime helps determine which processes are probable and which are not. The arrow of time emerges not from the equations, but from the way those equations respond to the initial configuration of the universe. A striking example of this interplay occurs during the formation of large-scale structures. When a region of space becomes dense enough, the curvature around it deepens. Matter flowing into the region follows curved geodesics. paths that represent the natural motion through space-time. As matter gathers, the curvature deepens further, strengthening the structure. This feedback loop leads to ever larger formations. The entropy of such a region rises not only because particles become more randomly arranged, but also because the curvature of space-time allows more energetic and dynamic configurations. Photons emitted during these processes travel along curved paths, carrying energy outward and dispersing information across the cosmos. The evolution of curvature and the rise of entropy become intertwined, each guiding the other as the universe moves from its smooth beginning toward increasingly complex structures. Radiation plays a central role in carrying entropy away from collapsing systems. As stars form, the light they emit travels across vast distances, filling space with energy that can never fully return to its original state. This radiation becomes part of the cosmic background of entropy, a record of irreversible processes that have shaped the universe since its earliest days. Every photon that escapes from a star, every neutrino produced during nuclear fusion, and every burst of light from a merging galaxy contributes to the ongoing climb of entropy. These particles stream outward indefinitely, spreading information that cannot be undone. Their travel across the expanding cosmos marks time passage in a way that cannot be reversed. The behavior of black holes adds another dimension to this picture. When mass collapses into a black hole, the curvature of space-time becomes so extreme that an event horizon forms, marking the boundary beyond which nothing can escape. The entropy associated with a black hole is immense, reflecting the vast number of microscopic configurations that correspond to its mass and energy. Although the interior of a black hole remains hidden from the outside universe, the surface area of its event horizon encodes its entropy. When two black holes merge, the area of the resulting horizon is larger than the sum of the original areas, increasing entropy significantly. This irreversible growth of black hole horizons is one of the clearest signs that the arrow of time is rooted in gravitational processes. It cannot be reversed by any known physical mechanism, and it aligns perfectly with the notion that entropy must rise as the universe evolves. The growth of entropy through gravity also shapes the environments that allow planets and life to form. Stars synthesize heavy elements in their cores, and supernovae distribute those elements into space. Planetary systems arise from the debris left behind after stars form, and life emerges in environments where energy flows in controlled but irreversible ways. Every chemical reaction within a living organism, every breath taken, every memory encoded in a brain relies on the availability of energy gradients produced by stellar processes. These gradients exist only because the universe began in a low entropy state that allowed stars to form in the first place. Without the smooth, early cosmos, gravity would not have had room to sculpt the structures that produce the energy flows required for life. The very existence of observers who contemplate the arrow of time depends on the fact that time has a direction, and that direction is written into the evolution of entropy. When we look back across the cosmic timeline, a single thread connects every irreversible event. From the collapse of the first stars to the merging of galaxies and the growth of supermassive black holes, each process traces its origin to the smoothness of the early universe. Gravity took that smoothness and amplified it into a universe rich with structure. Entropy climbed steadily as matter clumped, fused, collapsed, and radiated. Time emerged as the story of this climb, a one-way journey from improbable uniformity to the richly structured cosmos we see today. Although the laws of physics do not require time to have a direction, the evolution of entropy under gravity ensures that it does. The arrow of time is therefore not a universal decree, but a consequence of the universe beginning in the one place where direction was possible. With this understanding, we are now prepared to explore how gravity not only shapes matter, but shapes time itself. The next chapter will examine how the curvature of space-time influences the rate at which time flows, revealing a deeper connection between gravity and the temporal experiences of all observers. Imagine drifting near the surface of a massive star, watching the universe unfold with a clock in your hand. Now imagine floating far away in deep space, carrying an identical clock. If both clocks were built to the highest precision possible, capable of tracking even the tiniest fractions of a moment, you would still see them disagree. The clock near the star would tick more slowly than the one far from its gravitational pull. This difference is not a flaw in the design of the clocks. It is a fundamental feature of how time behaves in the presence of gravity. To understand why time itself can stretch and compress, we must step into the framework of general relativity, the theory that redefined gravity not as a force, but as a curvature of space-time. This shift in understanding reveals a universe where the rate of time depends on the shape of space, yet the direction of time remains untouched. Einstein's insight was that mass and energy tell space-time how to curve, and curved space-time tells objects how to move. In this picture, gravity is not an invisible pull, but the natural motion of objects along curved paths. A planet orbiting a star is not being dragged toward the star. It is following the straightest possible path within curved space. This curvature affects not only motion, but time itself. When the curvature becomes stronger, clocks run more slowly. The closer an observer is to a massive object, the deeper they fall into the gravitational well, and the more time dilates for them. This effect is not hypothetical. It has been measured repeatedly with extraordinary precision, using experiments involving atomic clocks flown around the planet and clocks placed at different elevations. Even a difference of a few meters in height on Earth's surface produces a measurable change in the rate of time. One of the earliest confirmations of this behavior came from the Pound-Rebka experiment, which measured how light changed frequency as it climbed out of Earth's gravitational field. The results matched the predictions of general relativity, showing that gravity affects the flow of time and the behavior of photons. Later, circumnavigation experiments involving atomic clocks carried aboard aircraft demonstrated that clocks in motion and clocks in different gravitational environments accumulate time at different rates. The global positioning system must constantly correct for these effects in order to function. Each satellite orbits high above Earth's surface, where gravity is weaker, and its onboard clocks run slightly faster than identical clocks on the ground. Engineers adjust for this difference so that navigation signals remain accurate. Without accounting for time dilation, GPS would drift dramatically, rendering it useless within hours. These experiments reveal a universe where time is elastic, stretching or compressing depending on the curvature of space-time. Yet this elasticity does not dictate the direction of time. Even though clocks run at different rates in different gravitational environments, they all run forward. The curvature of space-time modifies the speed of time, but not its orientation. This distinction is crucial for understanding the arrow of time. While relativity shapes the geometry through which entropy increases, it does not tell entropy which direction to go. The laws of general relativity are fully reversible, just like the equations of classical mechanics or quantum theory. If time were reversed in the equations, the curvature would guide objects just as consistently. The direction we experience is therefore not imposed by relativity. It emerges from the statistical behavior of matter evolving under these laws. Nevertheless, the connection between gravity and time remains profound. Time dilation means that different observers experience different stretches of history, depending on where they are in the cosmic landscape. Events that unfold quickly near a black hole might appear to take immense amounts of time to a distant observer. A collapsing star might seem to freeze at the event horizon when viewed from far away, even though time for the infalling matter continues normally. These effects show that the geometry of space-time influences the way observers witness the universe, even when the direction of time remains fixed. The passage of time is not universal. It is shaped by gravity in ways that become especially pronounced near the most massive and compact objects. The idea that time flows differently depending on location invites deeper reflection on how gravity influences the arrow of time. Although relativity alone does not define the direction of time, it determines the environment through which entropy grows. In regions of strong gravity, the processes that increase entropy unfold at different rates compared to regions with weak gravity. A supernova explosion near a massive black hole will radiate energy and raise entropy in a way that is profoundly shaped by the curvature surrounding it. Yet despite these distortions, the arrow of time continues to point from lower entropy to higher entropy. The curvature of spacetime becomes the stage on which cosmic evolution plays out, guiding the flow of events without choosing the direction. As we deepen our understanding of this relationship, it becomes clear that relativity and entropy work together to shape the universe we experience. Time dilation alters how long processes take, but entropy determines which processes occur at all. Gravity warps the flow of time, but the arrow of time arises from the improbable beginning of the cosmos. To move closer to a full understanding of this arrow, we must venture into the quantum realm, where fundamental equations remain symmetric, yet where the seeds of irreversibility begin to appear through the emergence of decoherence and the subtle asymmetries observed in particle behavior. Time dilation, in general relativity, becomes even more revealing when we consider how it interacts with the physical processes that unfold inside the universe. Imagine two observers watching the same event, such as a star passing near a massive object. One observer remains close to the gravitational source, deep in the curvature of space-time. The other watches from far away, where gravity has only a gentle influence. For the distant observer, the event appears stretched, unfolding slowly as the star moves through curved space. For the nearby observer, time flows normally from their own perspective, and they witness the event in what feels like an ordinary sequence. These differing perceptions do not arise from illusions or mechanical errors. They are a consequence of the fact that space-time itself dictates how quickly or slowly time passes. Yet despite these dramatic differences in rate, both observers agree on the direction of time. The sequence of events remains identical. The star approaches, interacts, and continues on its path, never reversing or contradicting the arrow that entropy sets. This consistency underscores a key principle. General relativity reshapes the tempo of history, but not its orientation. The laws governing curved spacetime allow for a universe in which clocks disagree, but they do not allow for a world in which entropy runs backward. The forward direction of time persists even when the rhythm changes. This is because entropy does not depend on how fast time flows. It depends on the number of microscopic arrangements available to a system and the tendency of physical processes to move towards states with more microstates. Even in regions of extreme curvature, where time dilation becomes enormous, entropy continues its upward climb. A collapsing star near a black hole generates heat and radiation that escape outward, increasing entropy even as the rate of time flow changes for different observers. Gravity modifies the stage, but the statistical behavior of matter sets the direction of the performance. Experiments involving atomic clocks illuminate this relationship with remarkable clarity. When identical clocks are placed at different heights on Earth's surface, the clock positioned slightly higher runs faster because it experiences a weaker gravitational field. This difference is tiny, yet measurable. A clock raised only a small distance accumulates more time than the one below it. These results confirm that time dilation is not simply a theoretical idea. It is a real and measurable aspect of how the universe operates. But if entropy depended on the rate at which time passed, then lifting a clock would alter the arrow of time, which clearly does not happen. Entropy increases in both locations because the direction of time is rooted in probabilistic principles, not in the tempo set by spacetime curvature. The behavior of spacetime near extremely dense objects reveals the depth of this distinction. Near a black hole, time dilation becomes so intense that an outside observer may see infalling matter slow to a near standstill as it approaches the event horizon. Meanwhile, the infalling matter experiences no such freeze. Its own passage of time remains smooth and continuous. However, whether observed from far away or from nearby, the entropy associated with the formation of a black hole continues to rise. The collapse generates radiation, turbulence, and heating, all contributing to irreversible processes. Once matter crosses the event horizon, the black hole horizon grows, increasing entropy even further. The arrow of time persists through every frame of reference, even as the measurement of time itself varies dramatically. This interplay between relativity and entropy becomes even more fascinating when we consider systems that rely on precision. Technologies such as global positioning satellites depend on clocks that must account for both gravitational time dilation and the time dilation due to motion. Engineers must adjust satellite clocks so that they align correctly with clocks on Earth's surface. Without these adjustments, navigation would drift and fail. Yet these corrections do not alter the direction of time. They simply ensure that different clocks agree on intervals. Entropy continues to increase in both locations because it governs the order of events, not the duration. In systems as simple as cooling metal or as complex as a star-forming region, the increase of entropy defines the arrow of time, regardless of the varying rates at which different observers measure that arrow. Even in extreme astrophysical environments, relativity and entropy work together in predictable ways. Consider an accretion disk surrounding a black hole. As matter spirals inward, immense friction heats the disk to extraordinary temperatures. This heating increases entropy dramatically as radiation pours outward. Meanwhile, the curvature of spacetime slows the flow of time for matter near the black hole compared to distant observers. Yet the rising entropy of the disk is something both observers agree upon, because it reflects an irreversible redistribution of energy and microstates. Time dilation changes how long each observer perceives the process to take, but not the direction in which the process unfolds. Entropy grows from lower to higher values in all frames, preserving the arrow of time. Understanding this dynamic reveals why relativity alone cannot explain the direction of time. The curvature of space-time can stretch, compress, and distort the rate at which time flows, but it cannot reverse the statistical trends that drive entropy upward. Gravity influences the canvas on which cosmic events are painted. Entropy determines the orientation of the painting itself. The arrow of time emerges from the improbable beginning of the universe and the overwhelming likelihood of matter moving into more probable states. Relativity shapes how this movement is experienced, but the movement itself is guided by deeper thermodynamic principles. With relativity woven into our understanding, we can now turn to the smallest scales, where quantum physics operates with equations that remain symmetric even as the macroscopic world becomes irreversible. The next step in our journey brings us into the quantum realm, where the seeds of irreversibility begin through decoherence, and where subtle asymmetries in particle interactions add new layers to the mystery of the arrow of time. The influence of relativity becomes even more striking when we examine how different observers describe the same irreversible process. Imagine a massive star nearing the end of its life, collapsing under its own gravity. For an observer situated far from the star, the collapse appears to slow as the star approaches the point where a black hole will form. Time dilation stretches every moment, making the final stages of collapse seem drawn out, almost frozen. For an observer falling inward with the collapsing matter, the process unfolds swiftly and without hesitation. Their clock ticks normally from their own perspective. Yet despite these two very different experiences of time passage, both observers agree on one crucial fact. The collapse is irreversible. The star does not spontaneously return to its earlier state. The entropy of the system increases in every viewpoint, and the formation of the black hole marks a new and vastly higher entropy configuration. This agreement reveals something essential about time direction. The arrow of time does not depend on how fast time flows. It depends on the statistical and thermodynamic structure of the universe. This principle extends far beyond dramatic astrophysical events. Consider two observers in everyday conditions. One stands at sea level, the other stands on a mountain. The gravitational field is slightly weaker at the higher altitude, so the mountain observer experiences time passing a little faster. But both observers watch ice melt, heated air rise, and batteries discharge in the same sequence. These processes always move from lower entropy states to higher ones. The order of events never reverses simply because one observer experiences a slightly different passage of time. Entropy dictates the direction and relativity shapes the rate, but the two phenomena remain distinct. The universe does not allow time reversal in one location and not in another. The growth of entropy unifies all frames of reference, anchoring the arrow of time in every region of space-time. This unity also appears in how information flows through the cosmos. Light carries information from distant events, crossing regions of strong and weak gravity, passing through places where time runs at different rates. As light travels, it may redshift or blueshift depending on the gravitational environments it passes through. Yet it always carries records of irreversible processes. The light from a supernova explosion may reach observers in very different gravitational conditions, but it always reveals a star that died, not one that undied. Even photons, influenced by the curvature of space-time, preserve the direction implicit in the process that generated them. When they finally reach an observer, they carry entropy and information that reflect a one-way history. Relativity also alters how energy is measured in different locations, but even these changes do not threaten the arrow of time. Near a massive object, energy levels shift due to gravitational redshift. A photon climbing out of a gravitational well loses energy, stretching its wavelength. A photon falling into a gravitational well gains energy. These shifts affect measurements, but not the sequence of events that produce the photons. A collapsing star still collapses. A burning star still burns. A cooling gas cloud still cools. The order of these events is preserved, even if the energy seen by different observers varies due to space-time curvature. Entropy continues to increase in all frames, reflecting the universal tendency of systems to move toward more probable states. This reveals an elegant and profound relationship. Relativity shapes the geometry of the universe, affecting how time passes, how light travels, and how gravity influences motion. But the arrow of time emerges from the statistical properties of matter and radiation, not from the geometry. Time direction is anchored in the fact that the universe began in a low entropy state, and every physical process since then has moved toward higher entropy. General relativity provides the stage for these processes, altering how their rhythms are perceived, but it does not rewrite their meaning. The arrow remains the same even when the flow of time differs. With this understanding in place, we can now turn to a realm where the puzzle becomes sharper. At the microscopic level, the fundamental equations governing particles and waves are fully time-symmetric. They allow evolution forward or backward without preference. And yet, when we observe the macroscopic world, we see a decisive arrow. This transition from symmetry to direction is one of the most fascinating mysteries in physics. To uncover the next layer of the arrow of time, we must step into the quantum world and examine how decoherence, measurement, and subtle asymmetries shape the emergence of irreversibility. At the smallest scales of nature, where particles behave like waves and waves behave like probabilities, the puzzle of time becomes even sharper. If we shrink our perspective down to the realm of atoms and electrons, the clear arrow of time that guides our everyday experience begins to dissolve. Processes that look irreversible on human scales suddenly appear perfectly reversible in the mathematics. A quantum state, evolving according to the Schrödinger equation, can move forward or backward in time with no contradiction. The equation itself contains no hint of direction. It simply describes how a wave function changes. Yet when we step back, into the macroscopic world, we see a decisive arrow. Ice melts but does not refreeze itself. Stars radiate energy rather than drawing it back in. People remember past events but not future ones. This contrast between quantum symmetry and macroscopic direction forms one of the deepest mysteries in modern physics. Imagine an isolated atom evolving quietly in empty space. Its wave function spreads, oscillates, and interferes according to rules that remain perfectly symmetric in time. If we reverse the motion of every part of this system, it would evolve backward just as easily as it evolved forward. Nothing in the quantum laws would prevent such reversal. But now imagine that the atom interacts with its environment. A photon strikes it. A particle collides with it. A detector attempts to measure its state. The moment this interaction occurs, the evolution of the system begins to look irreversible. The environment absorbs information. The possible outcomes become entangled with countless degrees of freedom in the surrounding world. This entanglement gives rise to a phenomenon known as decoherence, in which interference between quantum states becomes effectively impossible to recover. Decoherence makes quantum systems behave classically and creates the appearance of irreversible change, even though the underlying laws remain time-symmetric. Decoherence is not a mystical collapse. It is a physical process in which information leaks into the environment, dispersing across so many particles and interactions that no realistic experiment can gather it again. When a particle becomes entangled with air molecules, photons, dust grains, and the countless microscopic constituents of its surroundings, the combined system holds the full information about the interaction. But that information becomes spread so widely that it might as well be lost from the perspective of any observer. The system behaves irreversibly because recovering the original state would require controlling an astronomically large number of variables. This effective irreversibility is what makes the macroscopic world behave as though time has a direction. Decoherence thus acts as a bridge, connecting the time-symmetric laws of quantum physics to the time-directed processes we observe on larger scales. The quantum world also contains subtle asymmetries that further enrich the story of time. Certain particles, such as kaons and B mesons, behave slightly differently when matter and antimatter are compared. These behaviors involve violations of charge conjugation and parity symmetry, known collectively as CP violation. Experiments at particle accelerators, including measurements made at CERN, Bell, and Babar, have confirmed these asymmetries with exceptional precision. CP violation played an essential role in the early universe, helping ensure that matter survived while antimatter did not. Without this asymmetry, the universe today might contain equal amounts of matter and antimatter, leading to widespread annihilation rather than the formation of stars and planets. Yet, even though CP violation introduces a small preference in particle interactions, it does not set the macroscopic arrow of time. The symmetry of the fundamental equations still allows reversal. The arrow arises not from these small asymmetries, but from the statistical tendency of matter to move toward higher entropy. To see the limits of quantum asymmetries, imagine a system composed of decaying particles. The decay process gives each particle a finite lifetime, and the population of particles decreases over time. For a moment, this looks like a direction in time, but decay itself can be described in a time-symmetric fashion at the level of the equations. The direction appears because the initial conditions begin with a population of particles and end with their decay products. If we prepared the system in reverse, starting with the decay products arranged in a very special state, the reverse evolution would also be possible. But such a state would be extraordinarily unlikely. The arrow of time therefore reflects the rarity of certain initial configurations rather than any inherent temporal preference in the laws. Quantum measurements also illustrate how irreversibility emerges from symmetric laws. When we observe a quantum system, we create correlations between the system and the measuring device. Those correlations spread outward into the environment, becoming part of a vast network of entanglements. The quantum state evolves according to time-symmetric rules, yet the act of recording a result is irreversible in practice because the environment absorbs the information. We cannot unobserve the system or unwind the entanglement. The measurement appears to collapse the wave function, not because a fundamental law dictates collapse, but because decoherence makes all but one branch of the wave function inaccessible for future interference. This practical irreversibility mirrors the thermodynamic arrow of time. Both arise from the overwhelming difficulty of reversing microscopic details. The quantum world therefore supports the arrow of time in two ways. First, decoherence transforms quantum reversibility into practical irreversibility by distributing information across vast numbers of degrees of freedom. Second, subtle asymmetries in particle behavior played a role in shaping the early universe, influencing matter abundance without dictating the direction of time. What remains consistent throughout quantum theory is the absence of any fundamental temporal direction. The equations do not require time to flow forward. They allow both possibilities. The arrow emerges only when quantum systems interact with their environments, creating records that cannot be erased and processes that cannot practically be undone. With the quantum foundation in place, the connection between irreversibility and entropy becomes clearer. The arrow of time does not originate at the quantum level. It arises when quantum systems become entangled with a universe that began in a low entropy state. To understand how this statistical picture gives rise to the macroscopic arrow we observe, we must now turn to the realm of thermodynamics, probability, and the deep significance of coarse graining. As we follow the quantum world further, a pattern begins to reveal itself. Every quantum system evolves according to laws that are perfectly capable of running backward. Yet every real interaction with the environment creates a practical one-way street. This does not contradict the fundamental equations. Instead, it reflects how quickly information becomes dispersed among the countless particles that make up the surroundings. Even a single atom is never truly isolated. Photons scatter off it. Air molecules collide with it. Thermal radiation interacts with it. Each of these interactions entangles the atom with something larger, and that entanglement spreads outward in all directions. The universe records the interaction in ways that cannot realistically be reversed. This spread of information is the essence of decoherence, and it stands at the boundary between microscopic symmetry and macroscopic direction. Consider a simple example. A particle in a superposition of two positions interacts with a photon. The photon trajectory now depends on where the particle was. The particle becomes entangled with that photon, and the photon travels outward, possibly striking countless other particles or being absorbed by surrounding matter. The information about the particle original quantum state is now embedded in an enormous number of degrees of freedom. In principle, nothing stops the whole system from evolving backward. But in practice, no observer could ever gather every photon and every interaction and reverse them. The information has diffused too widely. The quantum system now appears to have taken a classical path, and any hint of its earlier superposition disappears. This transition is not a violation of quantum mechanics. It is the natural outcome of the impossibility of reversing microscopic entanglement across billions upon billions of degrees of freedom. This practical irreversibility reinforces the idea that the arrow of time is not a built-in rule, but an emergent property of systems with many interacting parts. Quantum systems do not collapse because a fundamental law forces them to. They lose coherence because information becomes irretrievably spread out. In a universe that began in a low entropy state, decoherence always moves in the direction of increasing entropy. Superpositions turn into classical outcomes, and those outcomes become records that point to the past. Even if the universe allowed perfect microscopic reversibility, the vast number of interactions occurring every moment ensures that decoherence builds an unmistakable arrow. Each interaction creates correlations, and each correlation becomes part of a one-way chain of events. Another subtle aspect of the quantum world emerges in the behavior of unstable particles. When a particle decays, we see what looks like a clear arrow. A collection of particles becomes a collection of decay products, but the fundamental laws describing this decay do not prohibit the reverse. If we arrange the decay products in an extremely precise and unnatural configuration, the system could evolve backward into the undecayed particle. Yet such a configuration would require arranging every particle in exactly the right position, with exactly the right energies, to an accuracy that defies comprehension. The arrow of time arises not because the reverse is forbidden, but because the reverse is unimaginably improbable. This is the same logic that drives entropy. The universe does not require disorder to increase. It simply contains vastly more disordered states than ordered ones, and systems follow the overwhelmingly likely path. The same principle applies to quantum measurements. A measuring device interacts with a quantum system, and information flows into the device, then into the environment. This creates a stable record. That record is not destroyed by the measurement. Instead, it becomes part of a chain of irreversible events. For a moment of time to have meaning, the universe must store information about previous states. But storing information always increases entropy. A memory, whether stored in a brain, a computer, or a grain of photographic film, requires energy to create and leaves a trail of microscopic change. These changes define the arrow of time. A memory points backward because the physical process of recording it requires the universe to move from a lower entropy state to a higher one. Even the well-measured phenomenon of CP violation reveals just how subtle quantum asymmetries really are. Experiments at CERN, the Bell experiment in Japan, and the Babar experiment in the United States have shown that certain particles behave differently than their antiparticles. These differences are small but important. They help explain why the universe contains matter instead of equal amounts of matter and antimatter. Yet even this fundamental asymmetry does not directly create the arrow of time. CP violation influences the balance of matter in the early universe, but it does not prevent the microscopic equations from running backward. The direction of time is not enforced by these asymmetries. It emerges when quantum systems interact with their environments and when those interactions occur in a universe that began in a state with ample room for entropy to rise. The quantum world does not contain a rule that forces time forward. Instead, it contains mechanisms that make backward evolution increasingly difficult as systems grow larger and more entangled. Decoherence ensures that quantum uncertainty becomes classical inevitability. Information disperses into the environment. Records form. Energy spreads. Probabilities shift toward states with more microscopic possibilities. All of this points toward a single truth. The arrow of time emerges from the way quantum systems interact with the universe, not from the equations that govern their isolated behavior. The mystery becomes clearer. Irreversibility does not arise at the quantum level itself, but from the statistical behavior of quantum systems embedded in a larger world. With the quantum picture now in focus, we can move to the realm of thermodynamics and probability, where entropy becomes the central player in shaping the arrow of time. To connect the microscopic world to the macroscopic direction we experience, we must now explore why entropy increases, why reversibility breaks down in practice, and how coarse graining transforms reversible motion into irreversible history. At the boundary where quantum behavior meets macroscopic reality, the final ingredient that shapes irreversibility becomes unavoidable. Every physical system carries countless microscopic details, far too many for any observer or device to track. When we describe the world, we do not record every particle position or every subtle correlation. Instead, we use broad categories like temperature, pressure, and density. This simplification, known as coarse graining, plays a pivotal role in converting microscopic reversibility into macroscopic direction. The equations governing individual particles allow time to run forward or backward without preference. But when we describe physical systems in terms of macrostates, we are grouping together enormous numbers of microstates. This grouping makes some evolutions overwhelmingly likely and others effectively impossible. As a result, time appears to move in only one direction. Imagine a box filled with gas. Each molecule follows laws that allow perfect reversibility. If we reversed every molecule velocity and position with infinite precision, the gas would trace its path backward, becoming more ordered. But no one keeps track of every molecule. Instead, we describe the gas by its temperature and pressure, both of which reflect averages over countless motions. These averages hide the microscopic details that would be required to reverse the system. When the gas spreads evenly through the box, it reaches a state with an enormous number of possible microstates. If we want the gas to spontaneously return to one corner, we would need the microscopic motions to align with extreme precision. Such alignment is possible in principle, but fantastically improbable. This is why the gas spreads outward and why it never spontaneously recoalesces into a neat cluster. Coarse graining ensures that the natural progression goes from fewer microscopic possibilities to many. This reasoning applies not only to gases, but to all macroscopic systems. When heat flows from a warmer object to a cooler one, the underlying particle interactions remain reversible. Yet the macroscopic description does not track every microscopic detail, and so the spreading of energy appears irreversible. The same is true for melting, mixing, burning, and every familiar process that unfolds in one direction. Underneath these processes lies a quantum world evolving symmetrically. But our coarse-grained view hides the information that would be needed to reverse them. As a result, entropy increases and the arrow of time emerges. Decoherence connects naturally to coarse graining. When a quantum system becomes entangled with its environment, the number of microscopic correlations grows astronomically. A complete description of the system would require tracking every entangled particle and every resulting correlation. No realistic observer can do this. Instead, the system is treated as part of a larger ensemble, and the detailed information is ignored. This ignoring is a form of coarse graining, and it gives rise to classical behavior. A quantum superposition becomes a classical mixture. Interference disappears. The system now appears to follow a path that cannot realistically be reversed. Decoherence thus amplifies the statistical arrow inherent in coarse graining, ensuring that macroscopic systems follow a one-way trajectory, even though their microscopic components obey reversible laws. These ideas become even clearer when we consider memory itself. A memory is a physical change in a system, whether it is a brain, a photograph, or a device. To create a memory, the system must move into a particular configuration among many possible ones. The formation of memory requires energy and increases entropy. Once the memory forms, it points backward because the physical process that created it increased entropy. We do not create memories of the future because that would require entropy to decrease and detailed microscopic alignment to occur. A memory, like any record, is a trace of an irreversible process. Time feels directional because our memories and records are rooted in the irreversible increase of entropy. In all these examples, the arrow of time emerges from probability. The microscopic laws allow for reversibility, but the statistical behavior of large systems makes certain evolutions overwhelmingly likely. A system moves toward macrostates with more microstates because such states dominate the possibilities. This trend is not written into the fundamental equations. It emerges from the enormous scale of the universe. With countless particles interacting in countless ways, the path of higher entropy becomes inevitable. It is not surprising that we never see a shattered object reassemble itself or a cooled cup of liquid spontaneously heat up. These reverse processes are possible within the equations, but absurdly improbable in the real world. Coarse graining ensures that the forward direction of entropy dominates entirely. When we combine quantum reversibility, decoherence and coarse graining, a coherent picture emerges. Irreversibility is not fundamental, it is emergent. The arrow of time appears when we describe systems in macroscopic terms and when information disperses across environments in ways that cannot be reversed. The universe began in a low entropy state, and this initial condition provides a vast landscape for entropy to increase. Every quantum interaction, every macroscopic process, and every flow of energy contributes to the rise of entropy. The arrow of time points in the direction of that rise. With this structure in place, we are now ready to follow entropy into the larger scale of cosmic history, where stars, galaxies, and black holes continue to shape the unfolding of time. To understand why the universe insists on moving from ordered states to disordered ones, we must begin with the idea that lies at the center of thermodynamics. Entropy is not a force or a substance or a physical law written into spacetime. It is a measure of how many microscopic arrangements correspond to a macroscopic condition. The more ways the particles within a system can be arranged while still producing the same overall appearance, the higher the entropy of that system. This idea, developed in the 19th century and refined through the work of Ludwig Boltzmann, forms the foundation for understanding why time has a direction. Although the fundamental equations allow motion to run backward, the statistical structure of entropy ensures that forward evolution dominates every observable process. Imagine a deck of cards freshly ordered by suit and number. This arrangement is special. It represents only a tiny fraction of the possible configurations of the cards. If we shuffle the deck, even a few times, we are overwhelmingly likely to reach a configuration that looks random. This randomness is not a new rule forcing the deck to disorder itself. It is a reflection of the fact that the number of random-looking configurations vastly exceeds the number of ordered ones. The same principle holds for all physical systems. A neatly arranged state contains far fewer microstates than a messy one. When systems evolve over time, they tend to move into states with more microstates because such states dominate the landscape of possibilities. This movement gives rise to the increase of entropy, and with it, the arrow of time. One of the puzzles that arose when physicists began studying these ideas is known as the Loschmidt paradox. If the microscopic laws are reversible, why does entropy consistently increase rather than decrease? If we reverse the momenta of all the molecules in a gas, the gas would contract into a small region, lowering entropy, even though this is never observed in nature. The answer lies not in the equations themselves, but in the improbability of setting up such reversed microstates. It is possible for the gas to reconverge, but only if the positions and velocities of every single molecule are arranged with extraordinary precision. The smallest deviation from this precise configuration would cause the gas to spread out again. Thus, while the equations allow for time reversal, the statistical likelihood of observing such a reversal is astronomically tiny. The forward direction of time is the direction of overwhelmingly probable evolution. Coarse graining reinforces this trend. When we describe a macroscopic system, we do not track the exact positions and velocities of every particle. We group together many microstates and describe them using broader variables like temperature or pressure. This grouping produces macrostates that encompass an enormous number of microscopic details. A system moving from a less probable macrostate to a more probable one appears irreversible because we have ignored the microscopic information required to reconstruct the initial state. Once information disperses, once energy spreads, and once correlations expand into the environment, we no longer have access to the details needed to reverse the evolution. Coarse graining thus turns microscopic reversibility into macroscopic irreversibility. Entropy also explains why the concept of cause and effect feels so deeply embedded in reality. Causes point to earlier states with lower entropy, and effects point to later states with higher entropy. When we record information, whether through memory or measurement, we increase entropy. The record points backward because the process that created it was irreversible. Our perception of time flow, with its steady march from past to present to future, emerges from this thermodynamic structure. In a universe where entropy had no room to increase, the distinctions between past and future would blur. Without low entropy beginnings, we would not remember the past, and the idea of predicting the future would lose meaning. Entropy provides the asymmetry that allows cognition, memory, and prediction to exist at all. Even the simplest processes demonstrate this idea. When a warm object transfers heat to a cooler environment, entropy increases because the energy of the system becomes more evenly distributed. The flow of heat is not enforced by a fundamental rule compelling warmth to move toward cold. Instead, heat flows because there are vastly more microstates corresponding to an even distribution of energy than to a concentrated one. An isolated system evolves naturally toward the most probable arrangement. The second law of thermodynamics does not forbid entropy from decreasing. It simply states that such a decrease is so improbable that it is never observed. The increase of entropy is the overwhelmingly likely path, and that likelihood becomes the arrow of time. This statistical nature of entropy illuminates a profound truth. The arrow of time does not arise from the laws themselves, but from the initial conditions of the universe. Because the cosmos began in a smooth, low entropy state, it had enormous capacity to evolve towards states with higher entropy. As time unfolded, gravity amplified tiny fluctuations into stars and galaxies, and these structures continued to raise entropy through fusion, radiation, and collapse. Every irreversible process reflects the fact that the universe began with room for entropy to grow. Without that initial condition, time would have no preferred direction, and the physical world would lack the asymmetry that makes history possible. With entropy, coarse graining, and probabilistic reasoning now clearly linked, we can see how the arrow of time emerges from the behavior of countless microscopic constituents. But to understand how this arrow manifests across the vast sweep of cosmic history, we must step back and examine how entropy has evolved through the grand stages of cosmic evolution. The next chapter will trace the journey of the universe from its smooth beginning through the formation of the first stars, galaxies, and black holes, revealing how the rise of structure is inseparable from the rise of entropy. Entropy becomes even more illuminating when we explore how probability guides the evolution of physical systems. Every macroscopic process we observe is the result of an overwhelming imbalance between the number of microstates that correspond to a disordered configuration and the number that correspond to an ordered one. The universe does not choose to move toward disorder. It simply explores the vast landscape of possible states, and the overwhelming majority of those states are more disordered than the states that came before them. This means that the forward direction of time is the direction in which the number of accessible microstates increases. The past is the region of fewer possibilities. The future is the region of many. The second law of thermodynamics, which states that entropy tends to rise, is therefore not a command, but a reflection of the immense statistical weight of higher entropy states. Consider a liquid cooling in a room. The liquid contains fast-moving molecules, while the surrounding air contains cooler, slower-moving molecules. Over time, the energy spreads from the liquid to the air. This is not because nature prefers equal temperatures, but because there are vastly more microstates in which the energy is evenly distributed than there are states in which the liquid remains warm and the air remains cool. The rise of entropy is the rise of probability. If the molecules happen to fluctuate spontaneously in such a way that the liquid regained its warmth at the expense of the air, entropy would decrease. But the probability of such a fluctuation is so tiny that it may not occur even once in the entire lifetime of the universe. This is why cooling is irreversible in practice, even though the microscopic laws would allow for its reversal. The concept of irreversibility also shapes how physical records form and why memories exist at all. When a record is created, information about the past becomes stored in the present through a physical process. That storage requires energy and increases entropy. A memory in a brain is encoded through chemical and electrical changes. A photographic image forms when photons alter material at the microscopic level. A printed document captures information because ink molecules adhere in patterns that correspond to meaningful symbols. All of these processes increase entropy, and because they do, the records they create always point backward. We do not generate records of the future because that would require entropy to decrease and microscopic details to align in arrangements far too improbable to occur. Memory and causality emerge naturally from the thermodynamic arrow of time. Entropy also clarifies why past events seem fixed while the future appears open. The past corresponds to a region of lower entropy where fewer microstates were available. Because so few microscopic configurations correspond to a highly ordered past, it becomes possible to trace that order forward and reconstruct earlier states. The future, however, contains vastly more microstates. Its possibilities are wider because there are more configurations that correspond to higher entropy. This asymmetry explains why we can often infer the past, but rarely predict the future with complete accuracy. The arrow of time points from low entropy to high entropy, and our experience of prediction and memory reflects this asymmetry. The statistical origin of entropy becomes even more apparent when we consider the role of coarse graining. When we describe a system at the macroscopic scale, we ignore most of the microscopic details. We do not care about the exact position of every atom in a room. We care about the temperature, which summarizes the average kinetic energy of those atoms. By ignoring microscopic details, we group many microstates into a single macrostate. The number of microstates within each macrostate determines its entropy. Higher entropy macrostates contain vastly more microstates and are therefore overwhelmingly more likely. This means that even if the microscopic laws are reversible, the macroscopic description will show a clear tendency toward higher entropy because we have ignored the information needed to reverse the evolution. Coarse graining transforms reversible motion into irreversible change by hiding details that would be required to restore earlier states. This probabilistic view also explains why attempts to define an arrow of time from the fundamental laws have repeatedly failed. No physical equation at the microscopic level contains an instruction that time must move forward. The direction arises only when we consider large numbers of particles and their collective behavior under coarse-grained descriptions. Even quantum processes that appear irreversible, such as measurement, become irreversible only because the environment disperses information in ways that cannot realistically be undone. The arrow of time emerges from the improbable nature of reversing a system composed of trillions upon trillions of interacting components. With these pieces in place, the connection between entropy and time becomes unmistakable. Time flows forward because the universe explores microstates that correspond to higher entropy. The past holds fewer microscopic possibilities and is therefore easier to describe and remember. The future holds an astronomically larger number of possibilities and is therefore less predictable. This statistical arrow shapes every physical process and every moment of experience. It defines what we call history, what we call memory, and what we call change. As we reach the end of this exploration of entropy and probability, the next step becomes clear. We must now carry the arrow of time into the vast timeline of the cosmos itself, tracing how entropy has risen from the first light of the early universe through the emergence of stars, galaxies, and black holes. The story of cosmic evolution is the story of the arrow of time writ large across billions of years. Entropy reveals its deepest meaning when we connect its rise to the way the universe itself unfolds. Every irreversible process, from cooling liquids to forming stars, follows the same statistical logic. Yet these processes gain their full significance only when we recognize how they build upon one another across cosmic history. The early universe began in an extraordinarily smooth, low entropy state. This smoothness created an immense range of possible higher entropy configurations, and the universe has been moving into those configurations ever since. The increase of entropy is not just a trend within isolated systems. It is the grand narrative of the cosmos, shaping the sequence of events that define the arrow of time. To see how entropy creates this sequence, imagine a giant landscape of possible microstates. The early universe sat at a high peak on this landscape, a narrow and improbable summit where matter was evenly spread, where temperatures varied only slightly, and where no complex structures existed. Gravity began to pull the universe off this peak, guiding matter into valleys and basins that correspond to states with more microstates. As matter clumped into stars and galaxies, entropy rose sharply because these structures contained far more microscopic possibilities than the uniform field that preceded them. Radiation from stars further increased entropy by dispersing energy throughout space. Every new structure added to the complexity and irreversibility of the universe, creating a path that pointed in only one direction. This one-way path becomes clearer when we consider the concept of microscopic reversibility. The laws of motion allow particles to trace their paths backward exactly as they trace them forward. But a universe filled with countless particles interacting in countless ways makes such reversal effectively impossible. To reverse the evolution of even a small cloud of gas, one would need to know and control every microscopic detail. Any deviation, however tiny, would cause the system to resume its forward march toward higher entropy. The forward direction is not imposed by the laws, it is imposed by probability. Once the universe left its low entropy summit, the number of available microstates increased enormously, and the evolution of systems followed the overwhelmingly likely route. Reversing that trajectory would require arranging the universe in an unimaginably precise configuration, one that has effectively zero chance of arising naturally. Coarse graining enhances this irreversibility. When we describe the universe, whether through astronomy, physics, or daily experience, we do not record every microscopic detail. A star is described by its temperature and mass, not by the position of every atom within it. A galaxy is described by its luminosity and shape, not by the detailed arrangement of every particle of gas and dust. By using macroscopic descriptions, we gloss over vast amounts of microscopic information. This loss of detail makes it impossible to restore earlier states, even though the microscopic laws would permit such restoration. The more complex the universe becomes, the more irreversible its macroscopic evolution appears. Coarse graining transforms the reversible equations of physics into the irreversible arrow of time. Irreversibility also explains why we perceive the passage of time in the way we do. Our memories form through processes that increase entropy. Recording a memory involves biochemical changes that cannot be undone without an equally improbable alignment of microscopic states. These changes create a physical trace pointing backward in time. That trace exists because the process that created it was irreversible. We cannot remember the future because no such irreversible process has yet occurred. Our psychological arrow of time, therefore, aligns perfectly with the thermodynamic arrow. Both arise from the fact that the universe started in a special, low entropy condition and has been evolving toward higher entropy ever since. The macroscopic world, with its patterns of cause and effect, depends entirely on this increase of entropy. A cause is an event that occurs in a low entropy state, creating conditions that lead to a higher entropy state. An effect is the consequence of this transition. If entropy did not increase, the distinctions between cause and effect would dissolve. Events would not unfold in a consistent order. The physical world would not produce reliable records or stable predictions. History itself would lose meaning. Entropy provides the structure that allows sequences of events to exist. Without it, there would be no arrow of time at all. Entropy emergence from probability and coarse graining ties together the microscopic symmetry of the laws and the macroscopic direction of the cosmos. The universe does not obey a fundamental rule that time must move forward. Instead, time gains its direction from the improbable beginning of the universe and the overwhelming likelihood of systems transitioning into states with more microstates. The arrow of time is therefore an emergent feature, arising from the combination of statistical behavior, gravitational structure, and the physics of information. With this understanding, we are now prepared to follow the arrow of time across the grand sweep of cosmic history, from the first light after the cosmic microwave background to the birth of galaxies and the formation of black holes. Entropy has guided the universe into its present complexity. The next chapter will trace this long story, revealing how each stage of cosmic evolution reflects the universe's deep drive toward higher entropy. To trace the arrow of time across the vast timeline of the cosmos, we must watch the universe evolve from its smooth beginnings into the rich and complex structure it holds today. The early cosmos was nearly uniform, filled with a hot plasma where tiny fluctuations were barely noticeable. Yet these slight irregularities, only a few parts in 100,000, contained the seeds of everything that would follow. As the universe expanded and cooled, atoms formed, light decoupled from matter, and the faint glow of the cosmic microwave background spread across space. From that moment onward, gravity began amplifying those tiny fluctuations, pulling matter into denser regions and sculpting the large-scale structure of the universe. Each step in this story marks an increase in entropy, driven by the natural tendency of matter and radiation to move toward more probable states. The arrow of time becomes visible not just in isolated processes, but in the unfolding of cosmic history itself. The first major transition in this history occurred during the era known as recombination, when the universe had cooled enough for protons and electrons to combine into neutral atoms. Prior to recombination, the universe was opaque because photons constantly scattered off free electrons. Once electrons joined with protons, the photons began to travel freely, filling the universe with the relic radiation we detect today as the cosmic microwave background. This moment marked the first time the universe produced a record that would persist for billions of years. That record shows a nearly uniform cosmos, yet with the crucial tiny variations that gravity would later exploit. Recombination did not increase entropy dramatically on its own, but it set the stage for the processes that would, by allowing gravity to begin shaping matter without constant interference from radiation. As time passed, gravity continued its slow and relentless work. Regions slightly denser than their surroundings drew in more matter, becoming the sites where the first stars would eventually form. These early stars, known as population 3 stars, ignited when pockets of hydrogen and helium compressed enough to trigger nuclear fusion. Fusion unleashed intense light and heat, flooding the surrounding space with radiation and pushing entropy upward. When these massive early stars reached the ends of their brief lives, many exploded as supernovae, scattering heavy elements forged in their cores throughout the cosmos. These explosions were among the most dramatic increases in entropy during the early eras of star formation. They not only redistributed matter, but also injected energy and information into space, enriching the universe with elements that future generations of stars and planets would inherit. The formation of galaxies emerged naturally from gravity sculpting matter into large-scale structures. Over hundreds of millions of years, the initial fluctuations grew into dense filaments, sheets, and clusters. Galaxies formed at the intersections of these filaments, becoming the luminous islands of matter we observe across the sky. Each galaxy contains billions of stars, gas clouds, dust, black holes, and dark matter. The formation of a galaxy represents an enormous increase in entropy because it rearranges matter into countless new configurations. As galaxies evolve, they merge, collide, and interact through gravitational tides, triggering bursts of star formation and unleashing new waves of radiation. Each collision spreads energy and increases disorder in ways that leave permanent imprints on the cosmic landscape. Observations from telescopes such as the Hubble Space Telescope, the Sloan Digital Sky Survey, and the James Webb Space Telescope reveal these processes unfolding across cosmic time, showing how entropy has risen through the formation and evolution of galaxies. The interplay between star formation and entropy becomes even clearer when we consider how stars convert hydrogen into helium through nuclear fusion. This process releases vast amounts of energy that radiate outward as light, heat, and neutrinos. These particles disperse, carrying entropy across space. A single star, burning steadily over billions of years, continuously produces entropy by turning ordered nuclear fuel into radiation. When many stars form within a galaxy, they collectively flood the surrounding environment with energy. These irreversible processes drive the cosmic arrow of time forward, illuminating the universe while steadily increasing its disorder. Star formation cycles mirror the rise of entropy at every scale, from the collapse of a gas cloud to the explosive end of a massive star. Black holes form at the endpoints of stellar evolution or through the merging of galaxies. When a massive star collapses, its core may become dense enough that gravity overwhelms all other forces, forming a black hole. Black holes represent not only extreme gravitational environments, but also the highest entropy objects known. Their entropy is proportional to the area of their event horizons, meaning that as black holes grow through accretion or mergers, their entropy increases dramatically. The growth of black holes marks one of the most significant contributions to the overall entropy of the universe. Supermassive black holes, found at the centers of galaxies, hold enormous amounts of entropy and continue to grow as matter falls in or as galaxies merge. These black holes anchor the cosmic structures around them, shaping the environment in ways that reinforce the direction of time. The universe's large-scale structure, with its vast filaments, enormous voids, and intricate clusters, reflects billions of years of gravitational evolution. Observations from deep surveys show that the web-like pattern of galaxies formed naturally from the smooth beginnings captured in the cosmic microwave background. This cosmic web illustrates the relentless rise of entropy as gravity transformed a uniform field into a complex arrangement of matter and energy. Each new structure, each merger, each burst of radiation reflects the universe moving toward more microstates, following the statistical path of highest probability. As cosmic history unfolds, entropy acts as the thread weaving all stages together. From the first stars to the formation of galaxies, from supernova explosions to black hole growth, the universe steadily moves toward more probable states. Time flows in the direction of this increase, and every structure we observe is a milestone along that path. The rise of entropy is not a small-scale phenomenon, but the guiding principle of cosmic evolution. To understand where this arrow leads, we must now follow the universe into its distant future, exploring the fate of stars, galaxies, and black holes as the cosmos continues its long journey toward higher entropy. As the universe continued to evolve, the delicate balance between expansion, gravity, and thermodynamics shaped the path along which entropy rose. After the first galaxies formed, the cosmos entered an era marked by ongoing star formation and the steady growth of structure. Stars were born in cold, dense regions of gas, radiating energy into space as they fused hydrogen into helium. This radiation increased entropy both locally and across vast distances, filling the universe with light that could never be recollected into its original form. Each photon that escaped from a star carried entropy with it, drifting outward for billions of years, adding to the irreversible record of cosmic evolution. Galaxies formed within the cosmic web grew increasingly complex over time. Smaller structures merged into larger ones, assembling clusters of galaxies bound together by gravity. These interactions stirred gas, triggered new waves of star formation, and heated intracluster material to temperatures reaching millions of degrees. This hot gas glows in X-rays, radiating energy outward in a way that transports entropy to distant regions of space. The growth of these massive structures is supported by observations from X-ray telescopes and deep sky surveys, which reveal how clusters develop through dynamic and violent processes. Every collision, compression, and heating event contributes to the rising entropy that defines the arrow of time. One of the most dramatic episodes in cosmic history occurs when galaxies collide. Although the stars within them usually pass by each other without direct contact, the gravitational tides unleashed during these encounters distort orbits and funnel gas into dense regions, triggering intense starbursts. Entire generations of stars can be born in the wake of a collision, lighting up the galaxy with energy that spreads across space. The shapes of galaxies change, their internal structures realign, and their final forms reflect the irreversible influence of gravity and thermodynamics. Observations from telescopes, such as the James Webb Space Telescope, show galaxies in various stages of collision, revealing how entropy increases as structures are torn apart, compressed, and reshaped. Another layer of entropy growth arises from the expanding universe itself. As space stretches, light waves emitted from stars and galaxies lengthen, lowering their energy through a process known as cosmological redshift. Although this redshift does not reduce the total entropy of radiation, it does contribute to the dilution and irreversible dispersion of energy across larger volumes. The expansion of space ensures that radiation continues to spread outward, never reconverging into its former concentrated state. The universe expansion therefore reinforces the arrow of time by thinning out energy densities and preventing the reversal of large-scale processes. The life cycles of stars deepen the connection between structure formation and entropy. When a star exhausts its hydrogen fuel, the balance between gravity and radiation shifts. Low-mass stars expand into red giants and shed their outer layers, leaving behind dense white dwarfs. More massive stars undergo dramatic collapses that ignite explosive supernovae. These supernovae scatter heavy elements into space, seeding future generations of stars and planets with the materials needed for complex chemistry and eventually life. The explosion disperses energy in a way that cannot be undone, sending entropy outward in all directions. The supernova remnant, expanding and cooling, reflects a new stage in the irreversible chain of cosmic events. The formation of planetary systems around younger stars depends on these earlier episodes of entropy production. Supermassive black holes loom at the centers of many galaxies, including our own. These immense objects continue to grow as they draw in surrounding matter. As gas spirals into the accretion disk around a black hole, friction heats it to extreme temperatures. This heating produces intense radiation that escapes into space, increasing entropy before the matter falls inside the event horizon. The growth of a black hole dramatically increases the total entropy of the universe, because a black hole entropy is proportional to the area of its event horizon. Larger black holes have larger horizons, and merging black holes form new horizons with even greater area. As galaxies collide and their central black holes merge, these events become major drivers of entropy growth. Observations of gravitational waves from merging black holes provide direct evidence of these processes, revealing how curvature and thermodynamics combine to shape cosmic history. The cosmic web, the large-scale pattern of filaments and voids, illustrates how gravitational processes drive entropy across vast distances. As matter flows through this cosmic network, it heats, cools, compresses, and disperses in ways that map the irreversible evolution of the universe. The structures we observe today are not static. They represent a moment in a long chain of changes guided by the interplay of gravity and thermodynamics. Entropy rises as galaxies consume gas, form stars, and expel radiation. It rises as clusters grow through mergers. It rises as black holes expand. This cumulative increase across cosmic scales defines the arrow of time more clearly than any isolated process could. The universe we observe today, filled with galaxies, clusters, stars, and black holes, reflects billions of years of entropy growth. Each structure marks a step along the arrow of time. As we look deeper into space, we look deeper into the past, witnessing earlier stages of this rise. Observations from deep sky surveys show how galaxies were smaller and more chaotic in the early universe, gradually evolving into the majestic spirals and massive clusters we see today. The direction of this evolution is the direction in which entropy increases. With the middle chapters of cosmic evolution now illuminated, we must follow the arrow of time even further. The structures we see today are not the end of the story. The universe continues to evolve, and entropy continues to rise. As we turn toward the next stage of this journey, we will explore how entropy drives the distant future of the cosmos, leading toward an era where stars fade, black holes dominate, and the arrow of time points toward a quiet and diffuse equilibrium. As cosmic history progresses into later epochs, the rise of entropy becomes increasingly tied to processes that unfold over billions of years. Galaxies age, stars are born and die. Black holes grow larger as they consume matter and merge with one another. Through each stage, the universe moves steadily toward more probable configurations, following a path shaped by gravity and thermodynamics. Yet even as structure flourishes, the seeds of the cosmos' long-term evolution are already present. Energy becomes more widely dispersed. Gas within galaxies becomes depleted. Star formation slows. The universe expands, thinning out matter and radiation. These trends show that time continues to move in the direction set by entropy, guiding the cosmos toward a distant future where structure gradually fades away. One of the most striking developments in this long evolution is the gradual exhaustion of gas reserves within galaxies. Star formation requires cold gas, and over time, galaxies consume or disperse much of the gas available. Some of it becomes locked in stars. Some is blown away by stellar winds or supernova explosions. Some falls towards central black holes. As the supply of cold gas diminishes, star formation slows, eventually reaching very low levels. This shift reflects a change in entropy dynamics. The birth of new stars produces radiation and increases entropy significantly, but when the gas reservoir becomes depleted, the pace of these entropy-producing events decreases. Even so, the remaining processes continue to increase entropy as existing stars burn their fuel and emit radiation across space. Clusters of galaxies provide another source of entropy growth. When clusters interact or merge, gravitational tides heat the surrounding gas to extreme temperatures. This hot intracluster medium emits radiation in the form of X-rays that travel into the universe, increasing entropy as energy spreads outward. The formation and evolution of clusters reveal how large-scale gravitational interactions contribute to the arrow of time across immense distances. Observations of galaxy clusters show that these systems continue to evolve, with gas cooling slowly over billions of years and sometimes falling inward to fuel new bursts of activity around supermassive black holes. Each of these processes leaves an irreversible imprint on the surrounding environment. As the universe expands, the distances between galaxies increase. Light traveling from distant galaxies stretches in wavelength due to cosmological redshift, reducing its energy. This redshift does not decrease the total entropy of the universe. Instead, it contributes to the dispersal of energy over larger and larger regions of space. Photons emitted billions of years ago continue to move outward, but their wavelengths grow longer as space expands. The spread of this radiation reflects a universe moving steadily toward a more diffuse and less structured state. The expansion thins out matter and radiation, reinforcing the trend toward higher entropy and weaker gravitational influence over large scales. Black holes remain among the most important contributors to entropy as the universe ages. Stellar mass black holes form from collapsing stars, while supermassive black holes at the centers of galaxies grow through accretion and mergers. When black holes merge, the area of the new event horizon exceeds the total area of the original horizons, increasing entropy significantly. This irreversible growth aligns perfectly with the arrow of time. Black holes also affect their surroundings by heating nearby gas through accretion processes and emitting powerful jets of radiation and particles. These interactions leave permanent changes in the environment, transporting energy outward and raising entropy. Eventually, the era of active star formation and galaxy mergers begins to wane. The universe transitions from a phase of rapid structure building to one of gradual decline. Stars exhaust their nuclear fuel and evolve into white dwarfs, neutron stars, or black holes. Over immense stretches of time, even these remnants cool. White dwarfs radiate away their heat, becoming cold and dark. Neutron stars slowly lose their thermal energy. Black holes continue to dominate the entropy budget, anchoring the long-term direction of cosmic evolution. Yet even as stars fade and the universe becomes darker, the arrow of time persists. Entropy continues to rise because matter transforms into radiation, because radiation spreads across expanding space, and because black holes merge and grow. The history of the cosmos is the history of entropy unfolding across every scale. Each irreversible event, from the collapse of a star to the cooling of a white dwarf, aligns with the statistical tendency of systems to move toward more probable states. As this chapter draws to a close, the picture of cosmic evolution becomes clear. The universe began smooth and low in entropy. Gravity amplified tiny fluctuations into vast structures. Stars and galaxies formed, radiating energy and increasing entropy at every step. Black holes grew into the largest entropy reservoirs in existence. The cosmic web stretched and thinned as space expanded. Every stage reflects the same underlying principle. Time flows in the direction of growing entropy because the universe began with room for entropy to rise. To understand the ultimate destination of this journey, we must now look far ahead, beyond the current era of galaxies and stars, into the future epochs where black holes dominate and the universe approaches thermodynamic equilibrium. The next chapter will explore how the arrow of time guides the cosmos into its distant fate. As the universe drifts into its remote future, the great engines that once shaped cosmic history begin to dim. The brilliant stars that once lit the galaxies have already burned through most of their fuel, leaving behind long-lived embers that shine faintly across widening distances of space. These ancient stars radiate their final warmth into the cold and ever-expanding cosmos, releasing energy that disperses into the background as entropy quietly increases. Galaxies, once vibrant with starbirth, grow sparse as their supplies of cold gas fade, and the remaining stellar remnants cool with unhurried certainty. The cosmic landscape becomes a gentler place, illuminated only by the fading whispers of dying stars and the faint glow of matter drifting through the dark. In this slow twilight of the cosmos, black holes rise as the dominant structures. Though born from the deaths of massive stars or from the merging of galaxies, their influence grows far beyond their size. Gas spiraling toward their event horizons heats to extraordinary temperatures, producing radiation that spreads across space before vanishing into the darkness. Each black hole anchors an enormous reservoir of entropy, far greater than that of the cluster of stars around it. Over unimaginably long spans of time, these titanic objects merge and grow, their event horizons expanding as gravity tightens its hold on the remnants of cosmic structure. Even the merging of black holes sends ripples through spacetime, waves that carry information irreversibly outward, marking another step along the arrow of time. As eons pass, even these grand events become infrequent. Galaxies drift apart under the accelerating expansion of space, and the distances between them grow so large that light from one galaxy may never reach another. Star formation ceases completely. White dwarfs cool into dark remnants. Neutron stars fade. Matter becomes rare, and interactions become faint. Yet entropy still rises as the remaining structures slowly radiate their heat into the void. Over extraordinary spans of time, even the largest black holes begin to evaporate through Hawking radiation. Their vast horizons shrink grain by grain, releasing their stored entropy into the universe as a thin mist of low-energy particles. When the last black hole finally fades, the universe transitions into an era where only a sparse scattering of radiation and elementary particles remains. In this final epoch, the cosmos approaches thermodynamic equilibrium. Its temperature becomes nearly uniform across inconceivable distances. With no gradients left to drive change, no remaining pockets of fuel, no collapses, no ignition of new stars, and no more gravitational engines strong enough to sculpt new structure, the universe reaches the quiet stillness of heat death. Entropy has reached its maximum, and though time continues to exist, the processes that once marked its passage have grown silent. This distant equilibrium is not destruction. It is the natural destination of a universe that began in extraordinary order and has spent its entire history drifting toward the overwhelmingly probable. The far future stands as the final testament to the arrow of time. What began as a smooth and improbable beginning has become a vast and diffuse sea where all gradients fade. This long descent sets the stage for a deeper reflection. If entropy guides the universe in a single direction, and if every structure and memory and moment is part of this movement, then what does it mean to say we are carried by this arrow? The next chapter turns toward that question, exploring the scientifically grounded idea that the universe is not simply moving forward in time, but falling through its own history. When we observe the universe evolving from its smooth early state toward its complex present and onward toward its quiet future, a profound image emerges. The cosmos seems to be descending through its own possibilities, moving from an extraordinary initial configuration towards states with ever greater numbers of microstates. This motion does not resemble falling in the usual sense, for there is no force pushing the universe downward in time. Yet the statistical structure of entropy creates a slope just as real as any gravitational descent. The early universe sat at the top of this slope, improbably smooth and highly ordered, containing only a tiny fraction of the microstates available to it. Time's direction arises because the universe has been moving away from that improbable peak and into the vast valley of possibilities stretching beneath it. In this view, the past is not simply behind us. It is perched on the high plateau of low entropy that the early universe once occupied. Every moment since has been a deeper step into the landscape of probability. Gravity magnifies this descent by shaping matter into structures that accelerate the rise of entropy. A smooth distribution has few microstates, but a universe filled with stars, galaxies, black holes, and radiation has extraordinarily many. Every gravitational collapse, every burst of fusion, every merger of galaxies is another step in the downward motion along the thermodynamic slope. The universe is falling not through space, but through its own statistical terrain. Quantum mechanics reinforces this interpretation. Decoherence disperses information into the environment, making reversal impossible in practice. Each interaction creates correlations that cannot be unmade, pushing the universe further into states with more microscopic possibilities. Memory forms because recording information requires entropy to rise. Causation appears because causes occur in lower entropy states, and effects occur in higher entropy states. Even our personal sense of time is woven into this downward motion. We remember the past because the universe has stored irreversible records of it. We do not remember the future because those records do not yet exist. This scientifically grounded picture reveals that the arrow of time is nothing more and nothing less than the path of the universe through its own probability space. We are carried along that path, living within the long descent that began when the cosmos was unimaginably smooth. To fall through history is to move with the universe as it evolves from its improbable beginning toward its most probable end. But to complete this understanding, we must gather all the evidence together and confront the final question. Why does the arrow exist at all? The arrow of time arises from a single extraordinary fact. The universe began in a state of astonishingly low entropy. From that improbable beginning, every physical process has unfolded along the path of increasing entropy. Gravity transformed smooth matter into structures. Thermodynamics dispersed energy across space. Quantum decoherence made records and memories irreversible. Coarse graining amplified the statistical tendency toward disorder. Every arrow we observe, from the cosmic to the psychological, aligns with this same direction because they are all rooted in the same initial condition. Yet the origin of that low entropy beginning remains the deepest unanswered question in physics. Nothing in the fundamental laws demands that the universe starts smooth or ordered. Many theoretical models attempt to explain this initial state, from inflationary dynamics to proposals involving quantum gravity, but the mystery remains open. What we do know, supported by observations of the cosmic microwave background, large-scale structure, nucleosynthesis, and black hole thermodynamics, is that this low entropy beginning is real and foundational. Without it, time would have no direction, structure would not form, and the universe would have no story to tell. The arrow of time is therefore not a built-in feature of the laws of nature. It is the emergent story of the universe evolving from its improbable past toward its overwhelmingly probable future. It is the descent from a pristine initial state into the rich tapestry of stars, galaxies, life, and eventually the quiet spread of radiation across expanding space. We exist in the midst of that story because entropy has room to rise, and because gravity and thermodynamics turn that rise into structure, energy, and complexity. As the universe continues its long journey toward equilibrium, we remain temporary witnesses to a brief era when gradients still exist and when time still feels like motion. The arrow of time is the imprint of the cosmos falling through history, carrying every atom, every star, every mind, and every moment with it. And though the mystery of its beginning remains unresolved, the arrow tells us something profound. The universe we inhabit is not static. It is a grand unfolding driven by the improbable gift of its initial state. This is where the story ends, with the recognition that time direction is not imposed from above, but emerges from the nature of the universe itself. The cosmos began in order, moves toward disorder, and in that movement writes the only history any universe like ours could ever have.